So, we are looking at if you just recollect from the last class, we are looking at effect of fire on materials, and then we are looking at concrete, and we said that cement hydrates, which is the binding material, right, which holds the which goes into the interstices of aggregate system. And this is true for asphaltic material also. These are actually particulate system bonded together, largely mechanically. Chemicals are very little. Chemicals, chemical bonding is very little. So, inert material, you pack them together and interstices is filled with some kind of binding material depending upon the nature of the requirement. For example, asphalt you need lot of deformation capability, plastic visco, so basically viscoelastic material. You want lot of deformation to take place in flexible pavements, whereas in case of concrete it is relatively works as rigid because it is a structural material mainly, although we can use it in pavement and other places. And essentially it is the binders which are initially in plastic state, in molten or plastic state sort of, so that you can mold it, and then either because of chemical reaction or because of these cases, in case of cement concrete is chemical reaction, it solidifies. In case of it is polymers, for example epoxy concrete, then you will have two component of the resin or something of that kind, the monomer system, and there will be a hardener, and it will polymerize to larger molecular weight and solidify. So, and some paints of course and similar sort of thing, there also we have got particulate system, and then they evaporate. So, basically essentially this kind of system you have got particulate system bonded together with some kind of binder. So, the binder is the one that gets affected by fire, because the inert aggregate system that is actually come from the nature would have formed at very high temperature, do not get effect, there is hardly any effect on them up to a fire temperature of 1000 degree, 1200 degree centigrade or so. So, as I mentioned in the last class, this is what I mentioned in the last class, the CHS is the calcium silicate hydrates, which is the one which has got some capillary pores and filled with water, and then it has got gel pores as we call it, which is actually this in the microstructure of itself of the calcium silicate hydrates, because they form a gelatinous structure with some they are layered structure with spaces in between the layer, which we call as gel space, and there could be adsorbed water there. So, as you some members CSH, this part is chemically bonded water of crystallization, this part is chemically bonded water of crystallization, all right, and rest all are, this is adsorbed water, and this is there is some capillary water. So, that is what I just mentioned in the last class, 100 degree centigrade to 150 degree centigrade capillary water will vanish, 200 to 400 degree centigrade adsorbed water will be lost, and this will result in shrinkage and cracks etc. due to shrinkage, all right. 400 to 600 degree centigrade, heat starts attacking the water, right, and chemically bonded water goes away, causing cementing property to be lost. This process is relatively irreversible, very little reversibility is there, mostly it is irreversible, all right. So, the 600 to 800 degree centigrade, the other part, because reaction of this materials which is called tricalcium silicate, we write it like C3S in cement chemistry, abbreviate them. When it reacts with water, right, some amount of water, so this would react, form CHS gel plus calcium hydroxide. So, calcium hydroxide is also a product of cement reaction, and this breaks down between 600 to 800 degree centigrade, and everything breaks down to calcium oxide and H2O. Therefore, an entire concrete system actually degenerates completely up to 800 degree centigrade. So, you will see spalling of concrete, if it is just chunk of concrete will come down because there is no bond, right. So, strength obviously beyond 300 degree centigrade residual strength reduces, and it goes on reducing till 800 degree centigrade, you will be left with very little. and if the aggregate constant contains calcium carbonate, that will get disintegrated around 600 degrees centigrade if the aggregate says limestone aggregate, and that is what I mentioned. So, this is the kind of relationship I mentioned last class, that there is a reduction in strength, there can be 20% stressed and then tested under compression. The other case would be you raise the temperature to that particular temperature, say 400 degrees centigrade, then test it under compression, then you find this strength. Now, this is the relative strength being talked about. One stands for ambient temperature, strength at ambient temperature, and this is unstressed residual. That means you have actually heated it up, cooled it down and then tested it. So, that is the lowest actually, because when you have heated it up, see when you have stressed it particularly, it is under compression, because we are talking mostly in case of concrete or similar material, it will be under compression, and because of heating there will be some amount of expansion. So, some stress might even get relieved, 20% stress you have given, then heated it up, there will be some stress relief. So, therefore, you might find that this is actually taking higher load, because you have already pre-compressed it, then you have heated it up and then testing it from 20% to whatever failure. So, there is a nullifying effect. There will be effects are like, first is a mechanical deformation because of the load, deformation due to shrinkage, there could be expansion. So, net effect of all this, net effect of all this is what you get the final strength as well as deformation variation. So, here essentially that is why it shows you higher. When you do not stress it shows a little bit lower, and it is unstressed residual, means unstressed residual means you have heated it up, lot of degeneration has already occurred, then you have tested it, obviously you get it least. And what is its implication? Implication is post fire load carrying capacity of the structure. So, what we see is post fire load carrying capacity of the structure would be much less compared to during fire or similar sort of thing, because normally load the dead load would be there, and imposed load, which is what we call quasi static, will not be there all the time, because consider a classroom, it is not full of all the students all the time. So, that is why the working load is much less than the design load. Design load is that load which will not be exceeded more than 5% of the time, characteristics load, that is what we take, and that too, that value we take by consensus of people. Working load is much less, rarely it goes to that level, it never. So, that is why this 20% they loaded and tested. Now, if you look at stress strain behavior, I think that is what we are looking at. There are 3 cases, as you can see, 375, 375, and there must be another 375, or only 2 cases being shown here. You see the issue, one is 0, another is 20% load, some cases 60%, already it is loaded, preloaded to 60%. So, when you have number of curves, say 200, this is not basically, this is preloaded to 20% possibly, this is preloaded to no preload, because that is what we said, it stress comes down, and this might be 60% of the strength you have gone, which means that you have already done some micro cracking. Now, if you have done micro cracking, heating will not close those cracks. Cracks are permanent deformation. Cracks actually manifest itself in form of permanent deformation, and little bit of expansion will hardly cause them to come back, fill in. That is not fully reversible, so it never happens that way. So, therefore, this is the thing. Similarly, 700 degrees centigrade, the cases are 700 degrees centigrade, you can see this. Now, thing is that whether loaded, partially loaded or not loaded, stress strain curve at low temperatures at 20 degrees centigrade, it is somewhere here. So, you have a modulus of elasticity. Now, you heat it up a little bit, then the elastic modulus does not reduce, may increase a little bit up to 300 degrees centigrade or so. Even strength it tend to increase. But after that, there is sharp fall and deformation capacity tend to increase. This is strain, micro strain. So, stress versus strain curve is like this. So, as if it is a kind of a a ductile behavior. Why? Because now as you have heated it up and then let us say loading it, lot of cracks have already formed. So, that cracks manifests itself in form of strain, right. Lots of cracks would have already formed, like tensile cracks would form in a compression cube like this. Cube normally when you load like this, essentially Poisson's effect causes cracks to occur like this, it bulges out. So, this would have already occurred, then you have heated it up. So, now this means the deformation, compression deformation, because Poisson's effect along this direction, there is a compression. So, when you raise it to 700 degrees centigrade, there has been already expansion in all directions, right. And the failures, now the failure has to start from one of those cracks or whatever has formed. Total deformation, if you look at it, you will find it much larger, but load it can carry is much less, because cracks are already there. And if you recollect or may not have studied, actually the strength is governed by weakest link. So, you have already cracks existing in the system, fracture will initiate from those cracks, largest cracks in fact. Griffith's theory, one can take cue from there. So, it will actually start propagating from largest crack at a critical stress level, and critical stress level is inversely proportional to square root of the size of the crack. So, you have already crack formed, larger crack formed because you have gone to high temperature. So, fracture would start at much lower stress level. So, so strength deformation is high, but it can't withstand anymore, because crack starts propagating easily, because already there are some cracks in this. So, that is why you see this kind of behavior, and therefore, modulus of elasticity which one would need in design, if somebody is doing a fire design, then you can see that modulus of elasticity relative value it reduces in this manner, some manner it reduces. Static test and dynamic test. What is dynamic test? In dynamic test actually you preload it, increase the temperature and do it again, right. So, static test is basically you increase the temperature, then do a static test only. Dynamic step, basically you put the load, somewhat load, increase the temperature to the required temperature, then again do the stress strain behavior. So, this is both these types of tests have been done, but either case you find the relative elastic modulus tend to come down, whether it is water cement ratio 0.4 or 0.6, they will come down. So, elastic modulus, you can understand this from previous diagram itself, the stress strain curve itself. So, modulus of elasticity will reduce down, strength reduces down while deformation capacity increases, but this really does not make much of a sense. It can take a lot of deformation, but basically because ductility we rely from reinforcement bar, not from concrete is supposed to be a brittle material in that sense. So, that is how concrete, effect of fire on concrete. Strength reduces, elastic modulus reduces, right, and they are all function of temperature. We will see that, we have some empirical equations available. Let us look at steel. Now, steel or metals, they are what are called polycrystalline. Metals are polycrystalline. How? Because you will have, if you look at the say steel, it is coming from molten phase, from molten state. So, what will happen is some sort of dendritic formation of solidification occurs, and it forms some sort of dendrite structure, which means there is something of this kind, one solid, one crystal, another crystal, and so on. So, they solidify into crystals, right, depending upon the arrangement of iron carbon FeC system. If you have iron and carbon or any other metal for that matter, right, and then you have nickel, etc., whatever you add, they form actually kind of crystals, because metals are known to have, say, atoms are assumed to be spherical bodies, and metals actually they pack with each other in a regular arrangement, and the space, void space in between those ones should be minimal. What we call packing density should be a specific value above which the crystal is stable. Packing density means 1 minus the voids in the system, packing density. So, percentage of solid divided by, or total solid divided by the solid divided by volume of solid divided by total volume, that is packing density. So, they pack, right, and therefore, different sizes of atoms make more stable, or their properties can be modified. For example, Fe alone is soft. So, you add carbon, so FeC system. So, there are different sorts of structures is possible, which I am not going to discuss here, but the point that I want to make you. So, to start with, they form somewhere solidification will occur, some point solidification will occur, and then it goes on expanding what we call in a dendritic structure form. So, you will have some sort of growth of this crystal around this initial nucleation point. Then you will another nucleation point and they will form. Now, orientation of the crystal, this is called a grain. A grain is crystals all having similar orientation, and this is another grain. This grain also has got crystalline structure, atoms arranged in regular form, but their orientation could be different than this. So, finally, like all gets filled in. So, you will have number of grains attached to each other with their boundaries, right. The boundaries forming change in crystalline structure from one grain to the other. Now, metals are said to be polycrystalline, that is why. Now, this will have all I am saying they should have regular arrangement, but there are defects. One place somewhere one of the atom might be missing, instead some other similar atom. For example, sodium lithium belong to same group. So, if sodium was to come, there could be impurity in the material, lithium would have gone in. This sort of thing happens. Actually, what happens is you have got atoms and their outer electron forms a kind of a electron cloud, cluster of electrons. There nobody's, it's free for all. So, when you apply electric current, they can move. That is why they are good conductor of electricity, heat, etc., etc. So, now my point is, what happens when you supply heat to them? The defects are there in the grain boundaries. Now, if you supply heat to a small, like up to say 200 degrees centigrade, crystal structure would not change. Crystal structure would not change. You start heating it more, there are effect on this grain structure itself. If you heat it up and cool it back, you get a new crystalline structure, right, or quench it, you might become a totally. For example, you might have heard of thermomechanically treated steel bars, right. There, when they come out of the rolling mill, you quickly quench them in water, cool it, or you might have seen blacksmith doing the same thing. He forms actually a hardened layer of what is called martensite. So, you see, if you heat it and cool it in certain rate, the properties crystalline structure changes. So, when you heat metals, that is what exactly happens here also. Up to certain temperature, nothing will happen, crystalline structure remains same. Beyond that, it starts affecting the property, because grain, the microstructure starts changing in some manner or other. Again, this is not a natural material. Steel is not a natural material, iron is available not in iron form in nature. So, if you go, because as I said, natural material you have to go to their formation temperature. If it is igneous rock, magma. Steel, as it cools down from its molten state, at different states, different crystalline structure forms. So, that is what it is. So, steel is an alloy on Fe, Fe and C. There is a thermal expansion up to 550 degrees, thermal expansion, and at 550 degrees centigrade, steel loses most of its structure, responsible for strength, etc., etc. So, if it is loaded, it starts warping, it will warp. Once cooled, it will regain some structure, but cannot regain the original structure and strength. So, Up to 200 degrees centigrade again steel, nothing happens to steel, but beyond this 200 degrees centigrade you find properties are different. Now, one simple way of handling steel is, okay, you assume that the moment the structure reaches 550 degrees centigrade, it will warp, hinge formation will occur here and there, and it will collapse possibly. So, we assume that if steel has reached 550 degrees centigrade, it is no good at all. This is very simple one. This is extremely simple way of looking at it. So, stress strain behavior of steel, mild steel for example, people have seen. So, you have up to 200 degrees centigrade, 200 degrees centigrade you have something of this kind, 20 degrees centigrade, 200 degrees centigrade yield strength comes down a little bit, but ultimate strength somewhat increases, but this ultimate strength somewhat increases. In other words, we can say up to 200 degrees centigrade strength reduction is very minimal. As you go further, this sharp yield point starts vanishing. This one 20 degrees centigrade you had something of this kind, this starts vanishing and it becomes something like this. 400 degrees centigrade something straight away is something like this, and upper yield point and lower yield point they have gone. 600 degrees centigrade is something like this. So, their property starts changing, because while at 200 degrees centigrade there will be expansion occurring, the crystal possibly would have tend to move away from each other, and dislocations should move accordingly. They might go to the grain boundaries, but still like pulling, if you have to pull it further, load it further, then it will resist more. But beyond 400 degrees centigrade or 600 degrees, this is what the behavior is. So, in such situation you take proof stress. Proof stress is what? You draw a parallel line, you draw a line parallel, you draw a line parallel, right? You draw a line parallel line to this curve at 0.001%. So, 1% or 0.2% proof stress you start looking at, they reduce down significantly. Remember, wherever you have a stress strain diagram of steel is like this, right? What you do? You see, you take proof stress for, instead of taking yield stress, you take useful strength as proof stress, simple case. So, what you do? You take 1% means 0.001, 1%, I mean 1% will be 0.01. So, you take strain as 0.01 and draw a line parallel to this, wherever it touches, that is the proof stress. That is what you use in steel design or RCC design for with let us say bars where you do not have sharp yield point. So, this is for high strength steel, this is for high strength steel, same behavior. Up to 200 degrees centigrade there is not much of a problem, but beyond 200 degrees centigrade, 600 or 400 degrees centigrade, you find that strength reduces significantly. Elastic modulus also would behave in the same manner. If you see this elastic modulus, initial elastic modulus is by and large same, but beyond that actually some of them elastic modulus also get affected a little bit. We have some empirical equations and we will look at them. Let us look at the material behavior first. What about timber? What is timber? Timber is essentially cellulose fibers embedded in lignin. You may call it as natural composite, cellulose fiber embedded in lignin. Sorry. So, what on heating they show behavior of charring. Now, little bit of, see, the polymers are, or any other, like you can have long chain polymer, right. So, you can have even, something like this hexagonal rings etc., repeating itself, long chain polymers. So, fibers are usually long chain polymers. Now, these ones, they are usually thermoplastics, means what? When you heat them up, they will slide over each other, each chain will slide over each other. So, a point comes when they start softening. When you heat up, they slide over each other and they start softening. So, that there's a and you cool it again, they can get into the same material. So, you can remold it. These are called thermoplastics. Now, supposing I have got 2-dimensional structure instead, 2-dimensional structure, then now sliding is not possible, and if it is 3-dimensional structure, sliding will further not be possible. So, you have complex 3-dimensional structures, such slidings do not occur, they are called thermosets. You can heat them up, then but molecule will break, pyrolysis would occur, they will burn, they will actually, and you still heat it to the ignition temperature, smaller molecules will come and they can react with oxygen, combustion process. So, timber, cellulose fiber, I said they are long chain, when you heat them up, some of those chains will break down in between, and at lower temperature they break down and they form actually cross-linked structure. In other words, they tend to become 2D or 3D structure from a 1-dimensional. So, charred product is actually not the wood, it is no longer just cellulose, but it is a thermosets type of behavior. You will have cross-linked structure. It does not burn so easily, its insulation quality is good. So, log if you have, you can see that its core hardly gets burnt. You have charring product at the periphery, at the surface, and this charred product, they do not allow heat to pass through them. They are relatively insulating and their burning rate, they now breaking them becomes a little bit more difficult, right. So, they do not soften, only you can disintegrate them at higher temperature. So, timber, this is one thing, timber shows charring. So, wood with cellulose embedded in lignin. The cellulose is long chain molecule, when heated the long chain may break and cross linking may occur, this is charring. Usually you will see them in logs. So, if long chains disintegrate, then volatile gases would come out and timber then burns. So, you have to break those chains at higher temperatures. So, you can see that timber, it has log form. If it is small pieces form, then charring would not occur, because surface area is very large now and heat would be reached everywhere in almost all parts of the wood crib or wood pieces. They will actually all get disintegrated simultaneously, but in a log, surface get charred before heat can enter inside, and that is why this sort of behavior. So, if large surface area of wood is exposed to heat, then pyrolysis takes place, that is what it is. So, charring occurs in logs where entire wood is not exposed to high temperature immediately. When occurs, some structure is retained. So, that structure is retained actually. Then plastics. Plastics, they do not have fixed melting point, as I said, thermoplastics, right, I already mentioned them. So, thermoplastics soften over a period of time and melt, and we call something like glass transition temperature. Now, what is it? Actually, it is something like this. If you see the specific volume, which is nothing but 1 by density, right, as a function of temperature, right, as a function of temperature. So, solid, they will expand, density will reduce. Now, in case of material where you have got sharp melting point, what will happen? Suddenly they will become liquid, suddenly they will become liquid, like ice, but then here the ice, of course, the volume of water is less, ice density is, it is less, therefore, it occupies more. But many other materials, the liquid occupies a more volume or different volume. So, it is a sharp change, while in plastic it is not so. In plastic it is not so, plastic it will be something like this, then it might change like this, soften, and then it goes like this. So, plastic softens because they slide, molecules slide, and then this temperature we call as glass transition temperature. So, Tg. Now, my point is I am not really going to the material science of it. The issue is Tg of thermoplastics is usually 70, 80, 90, 100, 140, 200 degrees, it is very low. So, there many plastics, thermoplastics will start softening, while thermosets will start disintegrating at their ignition temperature. So, your epoxy or epoxy concrete or similar sort of thing, or many times you apply epoxy repair material. Now, one has to be careful. You got to give some protection to it, so that if you have done that kind of repair in a building, in future it should not be vulnerable to fire, because they can withstand much lower temperature than normal concrete. Cement hydrates can really withstand better temperature, epoxy may not. So, the important feature of polymer is this, but other important feature of this material is that many of these plastics which are used, for example, your chairs and tables, if you have a plastic wrapping on them, and if they burn, they generate a lot of toxic gases, right. So, the smoke they produce, that can be fatal or dangerous to health. So, some of them even produce cyanide gases, because nitrogen would be there, carbon is very much there, hydrogen is there. So, they can produce HCN or cyanide gases, react with something. So, the risk of poisoning is more from this kind of thing, right. So, okay, so this is the materials on heating. Let us see a little bit with the structure just after this, right. So, okay.